Okay, so here is section 1.7, and I don't know if I can do this in one or two, because I really do want to I might break it up at 10 minutes and then do the remaining half. Okay, so first, before we start transformations, so now we're talking about transformations of functions. So in 1.6, you hopefully became comfortable with different types of functions, their graphs, their characteristics. So now, once you know that, then you can create new functions by transforming the parent, what we call those main functions, we call sort of the parent functions, right? And other functions that we look at are usually from those main functions until we get into this class won't go into trig, but we'll talk about exponential functions and log functions, and so they'll have their own sort of parental parent functions. But what you learn here with transformations will still apply to any function we use. So I just wanted to give you one more parent function, and this is the absolute value function here on the left hand side, and that's the graph of the absolute value function. And so although I have the answers written down, just take a minute and see if you can figure out, well, the domain is shown, but see if you can figure out the range where it's increasing or decreasing, and then we'll pause the video for a minute and then see if you can fill that in. Okay, so the domain is all reals, and I'll show you the other answers in 1 minute. But many graphs, so we can create many graphs from their parent functions, and we have different transformations. So vertical transformation causes the parent graph. So that's basically in order to create our new graphs, we look at our parent graphs and transform them some kind of way. So shift them up, down, left, right, or a combination of these. All right, so the vertical transformation causes the parent graph to go up or down vertically. Horizontal transformation causes the parent graph to move horizontally left or right. There are the answers on the left hand for range increasing and decreasing. Hopefully you got those correct. Number 3, translation, that causes the parent graph to shift left, right, up, down, or a combined shift. And then reflections are flip the parent graph over a horizontal or vertical line, and it mirrors the parent graph. Okay, so let's see. All right, so let's look at an example of a transformation, okay? And then we're going to go into the formal definition. All right, so to do this, first, you know the shape of the parent graph, right? And it's always, for all those parent graphs I showed you in 1.6, it's nice if you know some famous points on there, and that'll just help you when you're studying on this graph for x squared or whatever. So for x squared, you know, knowing that the origin is on the graph, so knowing that the origin is on the graph, and then maybe 1, 1, and negative 1, 1 is on the graph. That might be useful, and then you can draw your parabola, okay? And so we're going to make a table now that we know. So we know our parent f graph, which is f of x equals x squared, but our new graph is x squared plus 2. So its parent is x squared, but it's just we add in 2 on it. And so if we take some values, and I just picked some random x values, so 0, 1, negative 1, 2. Keep them simple. You don't have to make them too big, and maybe 3 or 4, so you can get sort of a nice shape of your graph. And this is, if we're looking at the parent graph, those are the output values. And if we're looking at the new graph, g of x, so when x is 0, g of x is going to be 2, because remember, g of x is x squared plus 2, right? And so we have those points, right? And hopefully you understand. So on f of x, let me just make sure. So on f of x, we have the point 0, 0. But on g of x, that point is when x is 0, g of x is 2. So I hope you know the difference. I condensed the table for space, but I hope you recognize the difference. So we see when we first draw the parent graph and then draw our new graph, we see that it's a vertical shift up 2 units, right? So we just took our parent graph and shifted it up 2 units, right? For b, so it's x minus 2 squared. So our parent graph is still at x squared, and we still plot values, and I would plot values just to make sure you're okay. And now from the parent graph, it looks like we took our graph and shifted over horizontally 2 units. So that's interesting. It's that x minus 2. Notice the difference too. That x, besides the plus or minus of 2, that x minus 2, notice that this is inside I'm sorry. So notice it's inside that exponent, right? Whereas, I'm sorry, let me go back. Whereas here, the 2 was on the outside. I'm sorry. The 2 was on the outside. It wasn't part of the exponent, right? But here it's part of it, and that causes our parent graph to shift horizontally 2 units. Okay? So let's look at this, and I know a lot of times when I give you a lot of letters and everything, it can be confusing, so I don't want to confuse you, but I want to give you formally what you're looking at. So I just showed you 2 examples of vertical and horizontal shifts. So what's going on is this. If C is some number, some positive real number, vertical and horizontal shifts in the graph of y equals f of x are represented as follows. Keep in mind that your f of x function will represent your parent graph. So there's a vertical shift c units up if the new graph, so h of x or whatever, anything other than your f of x, so whatever you name your parent graph, any other graphs are just a transformation of your parent graph, right? And so h of x is going to be your parent graph, which is your f of x, plus some c units. And that was what that example 1 was. But if we had f of x minus c, then we would shift it down, however, whatever c is represented. And then we have 3, a horizontal shift c units to the right. Now this is where we have to be careful. Now our new graph is f of x minus c. You see how that c is inside of the function? So here in 1 and 2, it's outside of your function comes first, and then you add or minus subtract c. But here your function is inside. Now this corresponds to that example 2. So when it's inside of your function, then it's if it's part of your input, I should say. If it's part of your input, then, because remember, whatever's in here, this is your input, right? So if it's part of your input, then you're shifting horizontal left or right. And if it's minus, counterintuitive. So if it's x minus c, then you're shifting it to the right. And if it's x plus c, then you're shifting it to the left. Okay. So for vertical shifts, if it's f of x plus c or minus c, you're shifting it up and down accordingly. But if it's f of x minus c, which is in number 3, then you're shifting it to the right c units, and if it's f of x plus c, you're shifting it to the left c units. Okay, I hope that makes sense. Definitely go back over the first 2 pages to see, but we're going to do some more examples now. Okay, so I would pause the video and write this down, or you can listen and then write it down later. So here we have use the graph of f of x equals x cubed, so that's our parent graph. We know that. We talked about how that looks, to sketch each function. So in A we have x cubed minus 1. So that 1, so c is equal to 1, right? So that, and in fact, that 1 is outside of our function, right? And so because of that, we know we're going to shift it. We're going to shift it vertically, and we're going to shift it down 1 unit, right? So the parent graph is in purple. So what I did was I put, again, it's good to know 3 points on your parent graph. So on the parent graph, I'm sorry, let's do this. So on my parent graph, I plotted using the points -1, -1, 0, 0, and 1, 1. All right, and here's another reason why it could be helpful to plot some points on your parent graph. If you know the points on your parent graph and you understand if your shift is up or down, you can take those points and to shift it. So if you plotted the points, if you plotted these 3 points and then sketched your cubic curve, your cubic graph, then you can just take those points and move each point down 1 unit, and there you have the graph in red, which is your g of x. Okay, I hope that makes sense. Please, hope I'm not confusing you all, but I hope that makes sense. Okay, so here we have a couple things. So like I said, it could be a combined shift. So we have a value inside of that function, inside with that exponent, I should say, and then we have something. So when I said inside the function, I mean with the exponent. Okay, think of it, if it's with the exponent, I shift left and right. If it's outside of the exponent, I shift up and down. Okay, so we have a couple things going on. So we have a shift upward. So here on my left-hand side, once you draw your parent graph again, here's our parent graph. We move the graph up 1 unit into the left 2 units. And again, if you have those, and they can keep them the same points. If you want to use the same points on all your graphs, you can. Some points might not come out as nicely on one graph than another, but if you want to, it's up to you. So keeping those same points, I can take each point and move the graph up 1 and then to the left 2, up 1. So here, look at this, that 0, 0, for example. Go up 1 and to the left 2, and you should see that it's that point right there. It's that point there, okay? Oh, let me stop this video here.